Welcome to The Explainer. Today we're asking what sounds like a simple question, but it might just be the most profound one in all of physics. What is time? I mean, we live in it, we feel it passing every single moment. But as we're about to see, the reality of time is far stranger and more mysterious than you could ever imagine. Okay, so let's dive right in. We all have this deep gut feeling about time, don't we? It's a one-way street. It flows from the past, through this exact moment right now, and off into the future. It never stops, and it never, ever goes backwards. You know this instinctively. If I show you a video of an ice cube melting into a puddle, it looks completely normal. But if I play that video in reverse, the puddle gathering itself up and freezing back into a perfect cube, your brain just screams that it's wrong, it's impossible. This intuitive sense of direction is what physicists call the arrow of time. And here's where it all starts to get really weird, because if you zoom way, way down to the level of individual atoms, the fundamental laws that govern the universe don't have an arrow of time. A movie of two atoms colliding and bouncing off each other looks perfectly normal whether you play it forwards or backwards. At the most basic level of reality, time seems to be a two-way street. And that is the heart of the mystery. Our everyday world insists that time only moves forward, but the microscopic laws that build our entire universe are perfectly happy running in either direction. So how on earth does a universe built from these reversible rules end up with a one-way reality for us? That's the puzzle we're going to try and piece together. To even begin to solve this, we have to completely destroy one of our oldest ideas about time, the idea that there's a single giant cosmic clock out there, ticking away at the same rate for everyone, everywhere. Isaac Newton believed in this absolute time that flowed perfectly for all, and then Albert Einstein came along and proved him wrong. Einstein's whole revolution in physics started with one wild idea. The speed of light in a vacuum is always the same for every single person who measures it, no matter how fast they're moving. Now that might sound simple, but the consequences are absolutely world-shattering. It means that two things happening at the same time for one person might not be simultaneous for someone else. This all comes down to your frame of reference, which is really just a fancy term for your unique point of view. If you're standing on the ground, that's one frame. If you're on a speeding train, that's another. And what Einstein realized is that basic measurements like distance and, crucially, time are not absolute. They are completely relative to your frame of reference. Check out this brilliant thought experiment, the light clock. If you're carrying the clock, you just see a photon of light bouncing straight up and down. Easy. But if I'm standing still, watching you fly by, I see that same photon traveling a longer, diagonal path. Now, since we both have to agree on the speed of light, that's the one unbreakable rule, the only way for that to be true is if time itself is passing more slowly for you. It's not an illusion. Time literally stretches. This just blows up the old idea of a universal clock. There is no single now that everyone in the universe shares. My now could already be in your past if we're moving fast enough relative to each other. Time, it turns out, is not a rigid background. It's a flexible, personal thing, woven together with the three dimensions of space into a single fabric, spacetime. All right, let's put this mind-bending idea to the test with one of the most famous head-scratchers in all of physics, the twin paradox. It's a classic for a reason. It really forces you to grapple with just how strange time can be. So here's the setup. One twin stays on Earth, the other gets in a rocket, flies off near the speed of light, turns around, and comes home. Because of time dilation, we know the traveling twin will have aged less. But hang on a second. From the traveling twin's point of view, wasn't it the Earth that was moving? So shouldn't the twin on Earth be the younger one? It seems like a perfect symmetry, a total paradox. The solution, the one thing that breaks the symmetry and solves the entire paradox, comes down to a single word: acceleration. Think about it. The twin on Earth just coasts along in one steady, consistent frame of reference. But the space twin, they have to fire up their rockets, speed up, slow down, turn around, and accelerate all the way back. You can feel acceleration. It's a real physical force. It's not relative. And that physical act of changing frames of reference is what makes their two journeys fundamentally different, and it's what resolves the paradox. What's really happening is that each twin is following their own unique path through space-time, and they each experience time passing along that path. Physicists call this proper time, and due to the weird geometry of space-time, the path that involves acceleration and turning around is actually a shorter path through time itself. The astronaut literally took a shortcut through time, and that's why they return younger. So, time is relative. It's personal. Got it.
But we still haven't solved our original mystery. None of this explains why time has a direction. Why do we remember the past, but not the future? Relativity doesn't give us the arrow.
To find that arrow, we have to look in a completely different area of physics. Not motion, not gravity, but thermodynamics, the science of heat, energy, and disorder. The answer is hidden in the famous second law of thermodynamics, and this incredibly powerful idea called entropy.
The easiest way to think about entropy is just as a measure of messiness. A perfectly stacked deck of cards has very low entropy. A shuffled deck has high entropy. The second law says that for any closed system, and our whole universe counts as one, total entropy, or messiness, can only increase or stay the same. It never, ever goes down. Things just naturally get messier. This is exactly why a drop of dye in water spreads out and never, ever spontaneously unmixes. It's not that it's physically impossible for all those molecules to randomly bounce back together into a little drop. It's just that it is so fantastically, mind-bogglingly improbable, you'd have to wait trillions of years to ever see it. There are just vastly more ways for things to be disordered and messy than for them to be tidy and ordered.
And here's the cosmic punchline. The arrow of time we all experience exists because our universe began in an incredibly special, highly ordered, low-entropy state at the Big Bang. And ever since that first moment, it's been on a one-way journey towards higher and higher entropy. Our perception of time moving forward is literally just us riding this cosmic wave of increasing disorder. So after all that, let's step back and ask our question again. What is time? Well, it's definitely not the simple, steady river we thought it was. It's a much more complex, much more slippery concept than that. The thing is, there isn't just one time in physics. We've seen at least three. There's the reversible time of fundamental particles. There's the personal relativistic time that's tangled up with space. And then there's the arrow of time, the thermodynamic time that emerges from entropy. And that's the one we actually experience every day. So the big takeaway from all this is that our most fundamental experience, that feeling of time flowing forward, isn't actually a fundamental part of reality at all. It's an emergent property. It's a consequence of the very special way our universe started and the simple statistical laws of probability.
And that view of time as just an unfolding of probabilities leaves us with some truly mind-bending questions. It challenges our ideas of cause and effect, of free will, of what real even means. If what we call the future is simply a more likely arrangement of particles than the present, was it ever really unwritten to begin with? And that is a thought that will stick with you for a long, long time.